Just like velocity, acceleration can, and honestly usually does, vary with time. However, the case of constant acceleration is very important for three main reasons. 1. The mathematics are particularly simple. That's kind of nice. 2. Constant acceleration occurs in a surprising number of instances, from whenever your car brakes to something falling near the surface of the Earth, to a whole host of other reasons. And 3, we can often approximate complicated cases as a succession of constant acceleration cases. And that makes we basically unlink the complicated behavior into a series of simple things which are then easier to solve together. Not surprisingly, the case of constant acceleration occurs when the acceleration is constant. Sort of duh. But when something is constant, it's always equal to its average value. And I want to stress this again every time it comes up. When something is constant, it's equal to its average value. Because in general, the average value has easy equations, whereas the varying thing has weird calculus stuff. So if we can take advantage, then we can make life easier, and that's what we do here. We say that the acceleration is its average value, but the average value of the acceleration is always the change in velocity over the change in time. So we're back into a simple algebraic case here, and we can do stuff with it. We can invert that equation and use the definition of delta v and delta t to get some connections. For concreteness, we're going to use the following symbols. We'll set the first moment at 0 so that delta t is just equal to the time we're talking about. And we'll take the later instant as just t. So instead of having ti and a tf, now we'll just say, and this will just make our symbols convenient, that we start at 0 and we have some time t as our time that we're talking about later than that. The velocity measured at the first instant will be v sub 0, y the 0, because it's the initial moment. Not necessarily that v equals 0. In fact, in general, not. And the velocity measured at the later instant, at the time we called t, is called just v. So we're stripping our subscripts to make the whole thing more generalizable. Remember that conceptually we're always comparing the results of equations, in this case the measurement of the instantaneous velocity at two different moments. We should also stress here that it is the instantaneous velocity at two different moments, not the average velocity during this time interval. Then the acceleration becomes delta v over delta t, but delta v is v minus v0, and delta t is t minus 0. So I suppose we could have written this out to say this simplifies a little bit to being v minus v0 over t. And then we can algebraically turn this around by cross-multiplying by t and solving, and we get our first equation that the velocity at some later time is the velocity at the start plus a times the time. As a quick aside, notice that that would be on a graph of v versus t. This is a line which has an intercept of v0 and a slope of a. So we're back into constant acceleration is linear on velocity plots. Sort of duh, and also that's good to see since we were using that before. What does that get us? Well, now that we have the velocity as a function of time, so if you tell me the state of motion at any moment in time, I can tell you how fast the object is moving any later moment in time. And that will be valid during the entire interval during which the acceleration is constant. For instance, a bottle rocket is launched upward with an acceleration of 5 meters per second squared. At the moment it passes the roof of the building, Alice is observed to be moving at 8.9 meters per second. How fast is it moving 2.5 seconds later? First, we should draw a sketch. That's almost always a good idea in physics. So here's our sketch. There's our building. And the 8 is historical. Here's our rocket crossing the roof at 8.9 meters per second. It's accelerating upward at 5 meters per second square. And we want to know what's its velocity 2.5 seconds later. We should be careful here. We're told the rocket accelerates upward at 5 meters per second square. So in case you're remembering from earlier physics classes, hey, what about the fact that gravity no, all that's balanced out, right? This is the net acceleration, which is upward at 5. We're still in kinematics. We're not dealing with dynamics yet. We're not talking about what else is going on. We're saying Alice observes an acceleration of 5 meters per second square. All right, after we draw our sketch, the next thing we identify the principles that connect the variables. For instance, we can use the constant acceleration equation that was just derived, that the velocity is the initial velocity plus at, and then we substitute and solve for whatever we care about. So we say v is the initial velocity, 8.9 meters per second, plus the 5 meters per second squared times 2.5 seconds. We notice conveniently and certainly, I guess obviously, that one of the seconds cancels that seconds. So we get meters per second in the second term as well. And then that's 21.9 meters per second. And then we should respect that we only have 2 digits of accuracy, so 21.9 becomes 22. We can manipulate the definitions of the variables into many different forms. The 5 most useful ones are given at the left. I abbreviate them with CAE 1, 2, 3, 4, 5, just to mean constant acceleration equation 1, etc. That's not standard. That's not anybody else's term. Don't use that on the AP exam, but it's kind of useful for us as a shorthand. In the interest of time for this video, I'm not going to derive these equations, but if you're interested, the derivations will be in a separate video on the class website. Here are the equations we come up with. The first is the one we just did. V is V0 plus AT. CAE2 says I can get the average velocity based on the initial and final velocities. This is actually interesting and useful and says that for constant acceleration, the average velocity, which we define through physics, is the same as the mean velocity of the start and the end. Right? Where does that come from? It's relatively easy to see, but we'll do it in the other video, so we'll just walk through these. The third one says that given this, I can also say that the initial position, or the final position at any time, is the initial position plus the average velocity times the time. That's really coming from the definition of the average velocity. And then putting these two together, let me know that the position is the initial position plus the initial speed times t plus 1/2 AT square. And that one, again, if you've taken a physics class, you know, this one is ridiculously common. Right, the position of a constant acceleration thing. Notice there's a sort of very special case. If you start at the origin at rest, which is again very special, then you get that x is 1/2 AT square. And this thing comes up a lot too, and you'll get used to it. Do keep in mind that while it's a useful thing, it is a special case where we start at the origin at rest. And then the last of the constant acceleration equations is this weird thing that combines all these and gets rid of the time. And the way you do it is, in fact, by combining them and getting rid of the time. It's just some crunchy algebra. And we find that the final speed squared is the initial speed squared plus twice the acceleration times the displacement. The key thing to note there is no t. That means that if you have a problem which you don't have the time and you don't care about the time, then this will be your one-stop shopping equation to use. You'll just go right to this and you'll be able to simplify stuff out. If you use the other equations, they'll work, they don't break, but they're more complicated, and often that's not going to be what you want. All right, the graphical interpretation is that on a VT graph, constant acceleration motion is a line whose slope is the acceleration. And again, that just comes back from the idea that A is the average, which is delta V over delta T, which is the rise over the run. So if we were to compute the rise over the run, we would get the acceleration. And since it's a line, we know the acceleration is constant. On an xt curve, constant acceleration appears as a parabola. And I want to stress here again, on an xt curve. Obviously, we just saw on a vt curve, it's not. But the signature of constant acceleration on a position plot is a parabola. And that's because we have x is something plus something times t plus something times t squared, which is the generic form of a parabola. So not surprisingly. And there's special things that go on here, and all the stuff you learned about parabolas you can use again, which is useful. This particular object starts with a negative velocity because, as we can see, the slope right around here is negative, but has a positive acceleration since the plot is curving upward. And we can find that usefully too, the sort of idea that if the graph is a smiley graph, then the acceleration is positive because positive people smile. And if the graph is a negative, then the acceleration is negative in that region because negative people frown. It's a dumb mnemonic, but it works to help you remember. If you want to look quickly at a graph, is this a region of positive or negative acceleration? We say, oh, the graph seems to be quote-unquote smiling, so it's positive. Notice again, only works on the position plot because the acceleration is the second derivative.